Hello, hello everyone. I'm here talking to you about like complex made bearable. That's a few ideas that we had at Nubank, like we're writing Clojure for the past 6 years or so. And this title is supposed to joke a little bit about the Rich Hickey's talk about simple made easy. If you haven't watched this talk, you probably should. It's an amazing talk. Several good ideas there that really inspire us to build the foundation of the Nubank software. And there are I think the most powerful idea on this presentation is that the language, that if simplicity is built into the language, or if the language has these smart defaults that, well, if you want to do something, the easiest way to do it is the better way, is the most simple way. So in Clojure, the default way to declare data is immutable data structure, so it's already a good default in that sense. And writing functions like a small set of standard library and having just a few syntax or construct embedded in the language, and everybody using these smart defaults in the language is really powerful to keep the complexity contained. So, at that talk, Rich Hickey was talking about doing a parallel with the other language construct, so it's trying to sell you probably that Clojure is good. I'm not trying to sell you that Clojure is good. I hope you already figured it out. But this is not the only thing. It's okay, so simple in Clojure is very easy to do, but what about the complex stuff? Every business you're solving for is complex by its own. It's inherently complex. So there's no easy way around it. Like making complex stuff being easy is not that of a thing, but you can make it a little bit more bearable by not mixing up some stuff. So this talk is about how to get the complexity in business that you cannot get away from and work more effectively on that. So before that, a little bit of context of Nubank. That's the company I work for. It's a pretty big use case. We solve for banking in Brazil. So banking is about holding people's money, is giving loans and using credit cards and giving points and so on. There are several complex stuff to implement that. And the complexity is there. It's you cannot move away from it. There are weird complex rules and weird complex tax requirements and regulations and whatever that people cannot bear by its own, the whole complexity around it. So we have to create ways to solve for that. And another thing that makes the problem worse is the scale that we are at. So Nubank grows very fast. And today we have 15 million customers. We have billions of requests and Kafka messages going a day. We have 350 microservices, 400 engineers, more than 50 engineering teams and product engineering teams. We run a sharded infrastructure to scale, so we have more than 15 shards now. And this also brings lots of complexity for us to solve. And again, one person cannot bear this amount of complexity by their own. So we have to create ways for the normal people, the normal engineer, to be able to work on that environment without being thrown away. So this led us to some ideas here. And one thing is that helps us deal with this complexity is that, well, software is a fractal. So if you look at software on each different level, abstraction level, it looks like the same. So this is the fractal definition here. So it's okay to be complex, but you can have like just enough complexity on each level so people can bear this kind of complexity on that level without being too confused about it. But we need to make sure that people are dealing with ideally just one complexity at a time so they can reason about it. And, well, I'll start with the first level here, is the functional level. On the simple made this talk, Hickey already told you about like the language level complexity, but now it's like the functional level. We have business logic that can be very complex, and we can model this kind of complexity using, for example, pure functions. That is the easiest construct we have on the language. And even if the function is complex, we have tools to help us, like Clojure spec. We can define some invariants and write some generative tests or example-based tests to help us deal with this kind of complexity over business logic. But the important stuff is, like, if we have pure functions, we have like a small amount of complexity there. It can be as complex as you want, of course, but you can contain that kind of complexity. And this is an example of a pure function. Like, it's basically you're taking some data and returning some data. You write some sort of operations over it. And this is a little bit complex, but it's a small complex. You can read it and reason about it in some small amount of time, hopefully. And you can easily test it as much as you want to test it, so you can also keep it safe or something like that. Other kind of functions that we have to write is controller-like functions. In this case, it's the functions that do the actual side effects, that do communicate with the external world. So these are functions that fetch data from the database or fetch data from other services via HTTP or some other protocol. And with that data at hand, it executes the pure business logic functions. So with the result of this business logic, we do produce the side effects, or altering the database, producing Kafka messages, or doing HTTP requests to other services, and so on. And this is also an example of a controller-like function. It's a little bit bigger, but it's basically I'm fetching some data from other services via HTTP, running two logics here, and then producing two Kafka messages. So this is a little bit complex. I'm wiring business logic and side effects here, but again, it's small enough that I can understand it given some time. And the dependencies of this function is like there is this HTTP and producer variables and inputs here. I do know that this controller function is dealing with Kafka and HTTP, so I can already see what are the complexities I have on those functions. So again, this is complex, but it's a small amount of complex, and I'm not coupling the business logic with the side effects here. So every time it's possible, we separate these two things. We have the logic functions describes the changes we want to make on the system, rather than having several functions that do logic and also change stuff. So it's easier to reason about if we keep those things separate. Okay? But even keeping them separate, we can compose them in a way that's easier to reason about. The other level is at the service level. Nubank runs a microservice architecture, so I'm talking about service here, but you can also read as like a model or something sort of construct that keeps you containing a part of your system. But when you're using service, the integration between services is rather complicated. It's a little bit complex. So we also need some construct to tame that. So first thing is like we do have services. They are infrastructure to run the functions we want to run. So in our case, there are like Jetty servers running Clojure functions there. And we want those services to have a single responsibility or a small set of responsibilities. So again, it's easier to reason about that specific service. And it only takes care of a few entities of your system, and often like related entities. So if you have a person coming to the code base, it's a small code base per unit, per service. So it's easier, even though the problem these services is solving can be very complex, it's again a small set of complexity, so we can have a better sense on it. And we have ports that are technologies or means to communicate between services or with the external world, like the database, like the Kafka cluster, like S3 or some file system. So these ports, in Clojure, we implemented it as components or as protocols that define a simple operation that people can reason about. And this operation means that you are communicating with the external world that can be very complex. But we're talking about like maps that have the context. So maps are data, and it's easier to reason about data rather than having complex structures here. And these ports can be implemented by libraries that are shared between all those 400 services we have. So we can evolve those libraries as much as we want to, and all the services benefit from it. And we do have the adapters part as well. That's the part where we tie those ports into the actual function calls. So we declare the schemas or the data shape for all the endpoints on this layer. And we adapt those schemas to an internal schema that service wants, assuming that we do want separate schemas on the outside, on the wire, and on the service itself. But we want to keep the handlers, the functions that actually handle HTTP calls or Kafka messages or so on, as just functions that receive maps. They should be as simple as we want, as we can have them. And they do wire the ports to the controller functions that do execute the logic. And they have access to all the components, so the dependencies are also explicit. Here's another example. It's probably a little bit small, but I have this balances function that I do receive an account ID and datomic. So I can fetch from the database all the balances from that account, and then I adapt this balance to a wire format. It's just a map, but it's a wire format for the map, and return it as an HTTP response. And the declaration of that handler is also based on just data. In our case, we use pedestal for that. But it's just about receiving a function that receives maps, delegates the call to a controller functions, and returns a map. So again, this can be a little bit complex. So it's complex defining the integration points, but it's contained complexity. You can reason about it easily because the hard work is inside the controller functions. And the key thing here is like you should not couple the controller functions, the functions that actually execute the logic, to the entry points. So you can have the same controller function receiving, processing a Kafka message or receiving it via HTTP. And your system, your functions should not depend on that. You should be able to separate these two things, and having the entry points calling the controller functions and the controller functions calling the other entry points in a way that they are not that much coupled. And also not coupling the entry points with the entry point handling logic with the technology you're working for. So if you have like a synchronous operations, like an HTTP request, you might as well use the same protocol for using an RPC library because they are basically similar. So you could use the same kind of handling function. And you can write like mocked versions of all of your parts easily if you follow this. So that's why we use components and protocols for that. You can easily replace the actual components from test versions that can help you test your system. And with all these ideas, we came up with something that we want to give a name that we call diplomat architecture. That's basically ports and adapters for functional that we had on Nubank. All the services at Nubank follow this architecture internally. And each layer here, we have one complexity only. So ports are dealing with the communication complexity, and they hide it in a simple protocol that everybody can use and understand. The adapters are dealing with the complexity of wiring the actual communication to the function calls, and they do that by functions that receive maps and return maps, so it's easier to reason about it. The controllers also do complex stuff, but they only deal with the wiring logic of the logics and side effects, so you don't put like heavy business logic on them, you just use it to wire those two. And you do that by composing functions. So it's also easier to reason about. It's simple constructs of the language. And we have the actual pure functions that do solve the major part of your business logic. And they are functions with simple Clojure constructs and standard library and whatever library you choose to use. So it's the most complex part, but it's also the one that has the simplest tools available. So it's the one that you can easily test and easily experiment on it. So this is the diplomat architecture, and we also apply that to microservices. So you have the service that helps us keeping the area small enough so people can understand it. You also don't want it to be too small, but you can have a small enough unit that people can understand, and you can implement domains over it. But now we have like several services, and we have the next level. That's the infrastructure level. We want this service to run somewhere, and for us to be able to use them effectively. And this deployment, provisioning, and running is a rather complicated matter as well. But we can have that complexity as well by having smarter defaults for service. So at Nubank, we already have this template of this diplomat architecture for every new service we want to build. And this template has a default set of good tools. So Clojure, Datomic, Kafka, Amazon S3, and so on. And the endpoints with metadata that we can use for everything. And this already solves for like 99% of the problems that we have. And if people want to do something else, they can. But the default way is already a good way to write software. So having these defaults, this default infrastructure or default service template helps us a lot to grow and solve new problems. And it also creates a kind of homogeneous infrastructure where every service we have in Nubank is Clojure and Kafka. Datomic, there are some services that don't use Datomic because they don't need databases. Not every service needs. Or we use some other database like Dynamo directly, but this already solves most of our problems. And we also leverage Clojure and Eden files to declare how the infrastructure should look like. So leveraging this, that every service is a Clojure service, we have a map that declares how to deploy that service into the infrastructure. And this is a very complex provisioning logic, infrastructure logic that most engineers don't have to know about it, because there is a map that declares what we want to do, and there is a team that's responsible for making this map happen in real life, and this team handles this kind of complexity that every other engineer don't have to. No other engineer has to deal with this kind of complexity. So creating this kind of abstraction and this declarative approach to the infrastructure help us get one of the most complex part of our system in an easier way. It's not that easy as well, but like it's easier than having to know how to deploy that. So we have good tools for people to use that kind of complexity. And also, when you use distributed system, you create a huge problem for yourself. So there is a tool that we have that is this contract-based testing. So the communication between the services are very complex to handle. And every service declares their contracts, the schemas they can handle. So the producers declare the schema they produce, the consumers declare the schema they consume. And we use a principle called tolerant readers, that the producers are strict about the data, but the consumers are not. They are loose on the requirements for data, so they only declare the pieces of the data they want to consume, and the producers declare it all. So it's easier to evolve the system, the services. So if you don't depend on the whole entity, only a few elements, it's easier to evolve the schema of the entity without breaking all the consumers. So, and since we have metadata on the endpoints, on the entry points and exit points, we can write a tool that automatically checks whether these two schemas are compatible. And This is an example on how to do this. This is a Kafka handling settings function or map that declares both the handler for that message and the schema that consumer expects. And on the producer side, we have something very similar to that. We also declare the topic name and the schema we accept. And we have a tool that there will be an session about it today. So if you want to know more about that tool, it basically generates examples from the producer schema and matches against the consumer schema for all the 400 services, for all the, I don't know how many endpoints, automatically at every commit, that every pull request we open on GitHub, on every time we merge to master. So we have some sort of guarantee that at least the services are speaking the same language. It doesn't say much about the logic itself, but at least the messages are okay. So it's easier to reason about it. And every service looks like the same. There are Lego pieces here, so it's easier to know, like, to go from one code base to another because they look like the same. And also integrating between the services is easy because it's basically either an HTTP call that looks like a function call or a Kafka message that looks like a channel. That's also like constructs that people are familiar on the language. So we can treat this kind of logic in a higher level, and it still works. So we have services talking to each other now, rather than like composing functional calls. We are composing HTTP calls or something like that. It's a little bit more complex because now these calls can fail, but again, like they look like the same, so it's easier to reason about from one service to the next. But this doesn't solve the next level. That's the actual business logic around it, the product that we are building. The product is very complex. And it's the normal thing here. Like every product that every one of you build is complex by its own. So there's no way around it. We need to solve that complexity. And the language itself doesn't help you much. That will not help you entirely on that. You have to be able to organize your code or organize your system in a way that you can evolve your product, learn more about your product, or solve the problems that your product needs in a better way. And the way you do it's like we have some parts of the systems that relate to a business domain or a small part of the system. And they do talk to each other. So we try to map this cohesive set of services that are on the same subject. And we use the Conway's law to assign that to a team. So the team handles the same kind of business logic. So it's easier for them to know what surface area of the domain that they need to know about. And we want that interaction between the domains to be as simple as possible, so one domain doesn't know much about the other domain. And we should aim to not couple those domains. But this is very hard to do if you don't know enough about the domain. And this was the reality for us when we started Nubank. We didn't know how a credit card worked, other than passing it on the street to buy something. So as we were evolving the system, we were learning more about the system and how it works. So the picture of the actual system is not as clear as this, unfortunately. But we are working on making it more like this picture, where the domains exist and they are kind of delimited, and they do talk to each other only via stable protocols or stable APIs. Creating a level where like we have products and platforms. And the differentiation here is a platform is something that will change very little. It's very stable and has some configuration points that we can do something about it, but the platform itself is a stable piece of the whole system that we can reason about it, and we can make sure that it does what it needs to do. And the products that we sell to people then are basically configurations over that platform. So we can split what is the actual product from what is a stable platform. And the reason to do that is that products change very often, and we want them to change. We want to experiment on products. We don't want to do that on the platforms, though, because we do want a stable system that we can scale to millions of customers and so on. So the ability of splitting these two, this is the hardest part on, on everything here, is what makes you, this is what gives you power to build a huge amount of products over a simple and well-documented set of platforms that have their APIs. And each platform on its own can be very complex, can handle a very complex business logic, but for the external world, they don't need to know about it. They need to know that they want to make a purchase, that they know how to receive a payment and process it, or that they want to close a bill and charge the customer. That's the only thing that they want, that the rest of the system wants to know. So having simple things to do, that's those complex operations, is key for us to be able to grow the system in a sustainable way and be able to create several products over it. But it's also the hardest part, because we have to really understand the domain here. So having some like the hammock time or thinking a lot about the problem helps you to do that. But there's no magic here. You have to understand your domain to be able to separate these pieces into cohesive parts so you can contain this kind of complexity. And finally, the software is a fractal. I'm not sure if you can relate to that first fractal here, but every layer that we have is pieces collaborating with each other or communicating with each other that we can compose. So, and if we can manage to contain the complexity on each level and expose a simple API to the next level, we have a better chance to have a bearable system that people can really understand it and evolve it in a better way, so you can have like multiple products, multiple teams, multiple people working on the system and being able to do so without having to know the whole system or having to be an expert on the domain to be able to work on it. So those are the ideas I wanted to tell about here. So thank you very much for listening to me up to this point, and that's it.